let me show you a simulation. This comes from the University of Nebraska simulations. We have a celestial sphere with a person marked out in a horizon diagram. I can rotate this celestial sphere around, north, south, east, and west. The blue line is the axis of the Earth. So there's the north celestial pole that I'm pointing at right now. The south celestial pole is also here. And the red lines mark out the summer solstice, equinox, and winter solstice paths for the sun on the celestial sphere. So for this person, who I've marked at 41 degrees north, which is the same latitude as our school, this person has the summer solstice path just as I described before, rising somewhere in the northeast, getting high in the southern sky, and then setting in the northwest. The equinox path rises directly east, gets high in the southern sky, sets directly west, and the winter solstice path rises south of east, gets highest on that day, just above south, and then sets somewhere on the southwestern horizon. But what about for somebody else on the Earth? Well, let me go to the opposite. Let's go to 41 degrees south. This is a person in the southern hemisphere. Notice how for this person, the northern celestial pole is no longer in their sky, but the south celestial pole is. And that the paths of the sun for a person on this day will take them to the opposite part of the sky. Instead of getting to its highest point above the southern horizon, for a person south of the equator, the sun will get to its highest point in the northern sky, above the northern horizon. The sun will still rise north of east and set south of west, but it will get to its highest point above the northern horizon. And so for this person, the equinoxes still rise directly in the east, set directly in the west, but on this day, on these days, on the equinoxes, the sun would get to its highest point in the north. That's very peculiar for somebody who lives in the northern hemisphere. You might not expect that. What about for somebody who lives at the equator? Well, in this case, if you live at the equator, and I'll try to get as close to zero as possible, for somebody who lives at the equator, it is possible for the sun to get directly overhead, and that occurs on either of the equinoxes. But the summer solstice still rises north of east and sets north of west, and the winter solstice still rises on the winter solstice, the sun will still rise south of east and then set south of west. On either of those days, the sun will not get directly overhead. Remember, for somebody at the equator, that only occurs on one of the equinoxes. If you live somewhere between the equator and one of the tropic lines on the globe, so all the way up to 23 degrees north or 23 degrees south latitude, then somewhere and at some time during the year, you would be able to get the sun directly overhead. When does that happen? Well, it sort of depends on what day of the year. So for a person, say at 17 degrees north, you may have to wait for a particular day of the year that's sometime between the equinox and the summer solstice for the sun to have a path that takes it to the zenith. But if you are north of 23 degrees, let's say 30 degrees north, then no path will get to zenith, although the summer solstice path will get very close to it. Okay, so that's what it's like for people on different locations on the Earth and what the paths of the sun is like.
This screencast is intended to help you learn how to draw celestial spheres for the sun's path, and in this particular case we're going to be looking at the location of the North Pole, 90 degrees north. We are going to start with the equinox date, and to find your angle of insolation during an equinox, you take 90 degrees minus your latitude. So in this case, 90 degrees minus 90. Don't tell me what the answer is. 0. So the sun will be at the horizon the entire time. And if we take a look at a starry night, we can see that here the sun is going to rise exactly in the east. I apologize, I had it set for the wrong location. So we take a look, we're going to make this 90 degrees north, and we're going to see it's going to rise, go back in time a little bit. It's going to rise exactly in the east and stay along the horizon the entire time, and then it's going to set in the west. And that's going to take it 12 hours to do that. So we have 12 hours of daylight, 12 hours of night on that particular date. So I would show it by rising sun exactly east, setting sun exactly west. Solid line for rising sun. And once I get past this point, it's going to be, that would be my setting sun. By the way, in either direction, it would be south because we're at the North Pole. So that would be for March 21st, September 21st. June 21st we'll do next, and you'll see why in a minute when I get back to December 21st. But if we take a look at June 21st, starry night. Let's change the date to June 21st, and we'll change the time to, not that it matters, let's everything be equal here, 6 a.m. Kind of the cool thing, I can just kind of scan the sky for the sun. Hey, there it is. And watch when I hit play, the sun, if we follow it, does not appear to rise or set at all, but instead circles the sky at the same altitude the entire time during the entire day for June 21st. Now, if we take a look at this little simulation that we've done so many times, that would be this orientation. For June 21st, you could see that the sun's rays, it's not possible for the sun to rise or set at the North Pole. They go straight across, and the North Pole is in 24 hours of daylight. The sun circles the sky on this particular date. Kind of cool, right? So how would we draw that? Well, we take a look at our equinox angle of insolation. We see it's 0. We know the sun's going to get higher in the sky by 23.5 degrees, so we're going to go 23.5 degrees this way, make my little mark. 23.5 degrees this way, make my mark. And now I do solid for, not that there's a rising and setting sun in this case, because there clearly isn't, but just to kind of give it some dimensional space. And then I take my date and put it there, June 21st. You might want to put it there, or there, but definitely not here, so there. Now let's take a look at December 21st. I'm going to switch it up a little bit, go back to this animation, and then you could see that if I go to December 21st, here, you can see that it's not possible for the North Pole to go into light at all. Therefore, it is 24 hours of darkness. As a matter of fact, if you go back in time, anything after September 21st, and you can see right there, the North Pole just starts to turn into darkness, and it will not see light again until, that's right, March 21st is when it starts to rise again. Kind of depressing, right? So, that's pretty easy to draw. Let's just show you in starry night, though, what that would look like. And let's just change the date to, in this case, it would be 12/21. It's at 22 right there, but we'll just make it 21. And I could just hit play. The stars and the moon still appear to rise and set because the Earth rotates on its axis, but there is no sun. The sun never gets above the horizon. It's below the horizon. So, the way how we would see that, it would be drawn like this. It would be below the horizon. So we don't have to worry about putting the December path on there at all, or some people would say at all.